All right. Hope everybody had a good weekend. Homework 1 has been submitted, and I've got a meeting with the homework grader today just to go over some instructions on assessing that. The feedback will be provided directly from within Blackboard, and I think typically what you can expect is about a 1-week turnaround on the assignments. And I'm not going to be scoring the homework, a homework grader will. But if you have any concerns, if you think there's been an error in the way that your assignment is graded, then you can get in touch with me and I'll take a second look at it. So the next assignment, homework number 2, is due a week from Wednesday. So you've got 9 days to work on that assignment. It's posted now, 10 problems. And we'll follow the same approach where the in-class exercises will introduce some ideas that then you'll practice again in the homework. And so if you wanted to get an early an early start on the assignment after today's class, then probably you'll be able to solve about 1/3 of those problems, and then after class on Wednesday you'll understand a little bit more. And of course it's all right to work ahead on the assignments, but don't panic if you see something on there that's unfamiliar, because chances are we just haven't got to it yet. All right, so we're still working through some ideas that are addressed in Chapter 1 of the textbook. I hope that you've got that already, and it's important to follow along. I'm going to do my best to explain things as I understand them, but it's always valuable to hear the same concepts from another point of view, so I do think it's important for you to flip through the book, read the definitions, and look at the example problems that are in there. So we're talking about the time value of money today and economic equivalence. And I think you already understand that money in the future is less valuable than money now. We've covered that a couple of times. And so what we're going to begin doing is some calculations of amounts of money as it's translated through time. And in doing so, we're going to apply a lot of the same terminology that we've already introduced when we discussed cash flow diagrams. So remember, on cash flow diagrams, it's not just arrows representing amounts, but it's also labels. So for example, when money is at time 0, meaning the present, then we could call that either P. Some texts refer to that as a present worth or a present value. There's actually a lot of different names for it. Sometimes it's referred to as a discounted cash flow, when you take all of the future revenue that your company may receive and you find out what's the present value of those future amounts that you're going to receive. Then that information is really important in trying to determine the value that should be assigned for a stock price. So if you're interested in investing, when you buy a share in a company, what you're buying is a claim to a portion of the future revenues and the future profits. So finding out how much those expected future profits are worth in the present is one component of finding the fair value of a stock. So these are all just different terms that refer to the same thing. Money now. Now, money in the future we label on a cash flow diagram with the letter F. Some texts call it future value or future worth. It just is different from money now because of the effect of interest and compounding and inflation. Those are all the same effect depending on whether you're looking at the costs of goods in the future, then you'd call it inflation. If you're trying to find out the value of your investments in the future, then maybe you'd think about it as a rate of return. If you're trying to find out the future money that you owe for a loan, then you could think of it as an interest amount. But money sometime in the future we label as an F if it's a single point amount. So it's not a recurring same amount every year kind of a cash flow. Whereas if it is a series of arrows that are the same height, which represent continuously the same amount year after year with no gaps, then that's referred to as a uniform series or an annual series, annual worth. Those are consecutive, equal, end-of-period amounts. Those are the basics. There are other things like gradients, which we'll talk about in future classes, but with these we can handle just about every cash flow problem and trying to find out economic equivalence. So what I mean by economic equivalence is when we combine an interest rate that applies to amounts that are changing over time, and we combine the idea that not only is the amount of money changing in the future, but so are the cost of goods, then we have to find out how to balance those two things to find out what amounts in the future are economically equivalent to today. So just as a simple illustration, if the interest rate is 10% per year, then you should be equally happy to receive either $100 now or $110 in 1 year, because the extra $10 1 year from now accounts for the difference in the time value of money. So they're economically equivalent. They're not numerically equivalent. I'm not saying that 100 equals 110. Obviously, those are two distinct values, but they're economically equivalent because in 1 year, $110 would purchase the same amount of things if I is referring to the inflation rate, meaning the cost of goods. So economically equivalent. We could calculate that amount using the formula F equals P times 1 plus I to the n. Now it's obvious to see when it's just 1 year that it's going to be $110 if I equals 10%. But sometimes it's less obvious if we've got a long time period between the two. And so you can use this formula to solve for F, the future amount, or if you know the future amount, you could use this formula to solve for P, meaning the present value, and determine the economic equivalence. You could also actually use it if you knew the future value and the present value and you knew the interest rate. You could solve for n. Like any one of these four variables could be the unknown potentially. And economic equivalence problems, I think in today's in-class exercise, I'm asking you to solve for a variety of different things. Sometimes it's the time, sometimes it's the interest rate, sometimes it's the amount either at the present or in the future. But the way these economic equivalence problems work, which is, by the way, there are plenty of them on the fundamentals of an engineering exam, the engineering licensure exam that you should take in your senior year, there will definitely be problems like this where you're finding out equivalent amounts some years in the future. So the symbols that will apply in these economic equivalence type problems, T is time, P present value, F future value, A an annual series, N a number of periods. Now N isn't always years, because sometimes if the interest is compounding monthly, for example, then what you would do is you'd find out the interest rate per period, which may be different than the interest rate per year. So for example, if the interest rate annually is 6%, and then n equals 12 periods, meaning each month, if you're going to substitute a problem like this into the formula that's on the whiteboard here, then the I that you should put in is the interest rate per period. So if this is 6% per year, then the interest rate per period would be 6% divided by 12, and so it would be 0.005, 0.5% per month. So sometimes the problems are going to be a little bit tricky, where the information will be given to you on an annual basis, but then just really casually it'll say monthly compounding. And then suddenly a switch has to flip in your mind, and you have to think that you're calculating the interest rate per period, and n would be the number of periods. So I'll give you some example problems where you have to do that so that you get plenty of practice distinguishing between the two. So here's an illustration using a cash flow diagram of economic equivalence. We had that example just a couple of slides ago saying that $110 1 year in the future is economically equivalent. So here this is saying if you make a deposit now of $100, and how do I know this is a deposit, by the way? Down. The arrow down means that from my perspective, it's an outflow. So a deposit now of $100 is economically equivalent to, now this is saying a withdrawal in 1 year. This kind of perspective would be if you were going to make a deposit into a bank, then how much could you take out of the bank after 1 year? So you just have to kind of roll with it sometimes, whether it's going to be both of the arrows are down, or if one of them is down and one of them is up, by reading the context of the problem statement. If the problem statement is asking how much can you withdraw in 1 year, then that would be like this, where the future value is an upward arrow. Sometimes it will be related to delayed payments, where you can either pay a certain amount now, or you can pay more in the future, and how much would that be in the future if you delayed paying your bill? In a case like that, both of the arrows would be down. So keep a close eye on whether it's an outflow and an inflow and what the problem statement is saying. But these two amounts are economically equivalent. You could withdraw $110 if you invested $100 at 10% per year. That's not to say a deposit is equivalent to withdrawal. This is just talking about the magnitude of the economic equivalence. All right, you can receive $100 in 1 year or a certain amount today. For I equals 10%, how much is the amount you should receive today? So P is unknown, F equals 100. Let's do this on the whiteboard. If the future value is 100 and P is unknown, and then it's saying the interest rate is 10%, so 1.10 will be 1 plus I, and then N, meaning 1 year, is just 1. So P is 100 divided by 1.1. So that's how we would find out what's the magnitude of it. This is how we'd illustrate this economic equivalence as a cash flow diagram. Turns out it would be $90.91. So that's how much the $90.91, if you put that into a bank account now, then it would turn into $100 after 1 year, and the interest would be added. So this is saying you can either get $100 in 1 year or a certain amount today. How much should you receive? Sometimes people think, well, it's just $90, because $100 minus 10%, but that's not how it works. We have to put it into the formula and solve for P. Turns out that it's $90.91 is how much you have to deposit, because if it was just $90, then 10% interest would be $9. And so at the end, you'd have 99. So you have to deposit more than $90 in order to have the interest amount turn into 100 after a year. There's going to be a kind of a standard way for us to summarize problems that will be really important when you're using cash flow diagrams and either the equation method or the table method that I talked about on Friday. So if you have a cash flow diagram like this, where the present amount is known and the future amount is unknown, what this basically is translate to is find F given P. And we put this in this order where the unknown is first and the known is second, so that if we summarized it as a ratio, we'd say this is F/P. And this is going to be important when we use the tables, because the tables are laid out as ratios. The ratio of the future amount to the present amount. And then you would multiply the known present value by the ratio to find out the unknown future value. So basically what you should know for now is that this kind of a cash flow diagram, we call it F/P. F in the numerator, P in the denominator. Okay, so then what would this be? Just think, maybe write it in your notes. If the known is F, P is the unknown, then find P given F. So P is in the numerator of the ratio, F is in the denominator, F is the known, P is the unknown. This is a classical representation of find A given P. Now what you'll notice is that the annual series starts at year 1. The annual series does not start at time 0. And if there was a gap, like if we had a cash flow diagram that had an outflow in year 0, and then nothing happened in year 1, 2, 3, 4, 5. If it was like this, we can still call this an annual series, but the fact that there's a gap year, we couldn't just immediately find out what is the present value. This is like the classical representation of an annual series, is that it is 1 year, it begins 1 year after the present. So if we had something like this, what we'd have to do is we'd have to find out what's the equivalent of this annual series in year 1, and then we would move it from year 1 to year 0. So that's just kind of an early glimpse of what we're going to be doing in the future. But here, if we had this kind of a cash flow diagram, we'd say find A given P. A, the unknown, is in the numerator. P, the known, is in the denominator. Here, it's the reverse, where we're finding P given A. A is known, P is unknown. So try to commit this method to memory, like what's in the numerator of the ratio and what's in the denominator, because it'll be useful as we get into solving some of these more complicated cash flow diagrams. All right, let me bring the in-class exercise up on screen, and then I'll hand that out as well.
That's super weird, because mine, like, they just print it and they give you it right there. Maybe it won't matter to you. Well, even if it literally goes in one page, it will probably be one page.
Okay, so the first problem is just asking you to do a cash flow diagram. And I wanted to point out that when you have an annual series and also a single point value in the future on top of it, there's a couple of ways to represent that. Ordinarily, what I prefer to do is leave the two separate and just have the single future value as an amount that's on top of the annual series. And so let me show you what I mean about that. Okay, so it's going to cost $550,000, so that's a single outflow at the present, because purchasing the equipment is the event that kind of kicks off this series of cash flows. So it's at time 0, and then that equipment generates an extra revenue of $85,000 for each of 6 years. So 1, 2, 3, 4, 5, 6. Boy, that's a sloppy cash flow diagram. The arrows are roughly the correct height. They're roughly equivalent height. The annual series applies to all of these arrows, and then there's a single lump sum future value of the machinery being sold as scrap for $50,000 at the end of the 6th year. So either you can have a 6-year annual series with a single lump sum on top of the annual series, or if you want, you could have a 5-year annual series, and then the 6th year is a lump sum of $85,000 plus 50. So that would be $135,000 in year 6. The reason why I prefer to keep them separate is just it's a more accurate representation of what's actually happening. And these cash flow diagrams are just quick ways to translate a word problem into like a visual representation of reality. And so what is really happening is that the source of this annual series is the annual revenue from operating the equipment, and that's separate from the lump sum salvage value that occurs in year 6. So that's why I keep them separate, is that that money came from separate things. Does anybody have questions about the first problem? Okay. The problem didn't say anything about interest rates, so we didn't define an I value anywhere on the cash flow diagram. That's okay. All right, so the second problem is saying you want to receive $95,000 next year from an investment account that offers 9% annual interest. So draw a cash flow diagram, and then how much should you deposit today? So the cash flow diagram is what you want to do is deposit some amount now, arrow down, P equals unknown. I equals 9%. That can just be somewhere in the proximity of the cash flow diagram, and then we want to withdraw $95,000 in 1 year. I should have written the number 1 somewhere next to that tick mark. So the amount that you should deposit today is $87,155.96. So you need to be accurate to the nearest penny to get the right answer. Don't round off to the nearest $10, the nearest $1. We'll take it to the nearest penny, which we can do when we've got the equation method. Okay, now the third problem is about jet fuel. Is it better to buy it and store it, or to deposit a certain amount of money today and then just have the money available in the future when the gas is more expensive? I thought of this problem at the beginning of the pandemic. Do you remember how cheap gas got at the beginning of the pandemic? I think it was less than $2 if I remember correctly. I took a photo of Sheetz over by the mall because it just surprised me how cheap that it got. At the time I thought, man, I wish I had just a gigantic tank in my backyard and I could store thousands of dollars of gas, because I knew it's not going to stay cheap. But what if you did something like this where you had to pay a storage fee, or you could just put that amount into a savings account and then see how much fuel you're able to buy in the future, or how much money do you have left over. So there's a couple of different ways to figure out which option is better. So this is the first of the cases where I'm asking you to make a decision, put together some sort of an analysis that illustrates which approach is cheaper or what has the most value. So here's how I looked at it. I said, if I buy the fuel now and then I pay $13,333.33 a year to store it, then the money that I need to have available for that is about $260,000. Now, there's a little bit of an asterisk there, because this storage fee, the question is, do I have to pay the storage fee now at the present, or can I pay the storage fee each year that the fuel is being stored? Because if I could pay it each year that the fuel is being stored, then maybe I could invest some of the money to have a certain amount of funds available for the storage fee. So that complicates things a little bit. Let's just say that what we're going to do is have all these dollars available at time 0. $260,000 available at time 0. So if instead of buying the fuel and then paying the storage fee, what if I just put that money into an account that's earning 7% interest? How much money would be at in the account at the end of 3 years? It would be $318,511. So that's a lot of money, but is it enough to buy the fuel that we need to purchase? Well, 100,000 liters of fuel at this higher future cost of $2.65 per liter means that we'd be paying $265,000. So yeah, you'd have enough money left over. Actually, you'd have $53,000 in excess funds. So of these two options, is it better to buy the cheap fuel and store it, or is it better to invest money now and then buy the fuel at the higher price? It seems like buying the more expensive fuel is the way to go in the future. All right, so that's problems 1 through 3. That still leaves you with problems 4 and 5. Well, 4 and then just an alternate method of solving 4. So I'll pause and give you a chance to continue working on that. Okay, I've got the solution to problem 4 up on the screen. We're moving money through time, and it needs to be compounded a certain number of years. So the approach here is saying this $12,500 that's in year 1, how many years does it need to be compounded into the future until it gets to year 4? So you can just count. If you were going to find the equivalent value of $12,500 in year 1, you want to find out if it's compounding at 5% per year, what is that amount by the time it gets to year 4? Then the number of years it needs to move is 1, 2, 3. So this amount that's at year 1 is equivalent to $14,470.31 if it's compounded 3 years into the future. The $12,500 that's in year 2, it is moving 2 years into the future to get to year 4. So same formula, future value is equal to present value multiplied by 1 plus I to the power of n. So the $12,500 in year 2, it only contributes $13,781. So it hasn't compounded as many years, and so that's why the amount is less compared to the amount that was at year 2. So this amount at year 3 is just moving a single year to get to year 4. And then the amount that's at year 4, it doesn't experience any compounding. So we don't have to account for the interest that's earned at year 4 because it's in the same year as that lump sum. So 53, 876, and 56 cents. If you use that equation, find F given A, then you should get the same thing. You multiply A, the amount of the annual series, by the value of the ratio. So in the brackets here, it's 4.310125. So multiplying that by the 12,500, we get the same 53,876. And when we start doing things on spreadsheets, we can automate those calculations by just putting in a formula one time and then dragging the formula down row by row. So here what I did was I created a cash flow table. This is just representing the 12,500 inflow each year. And you see it's in a given year, but then I've also come up with an alternate time axis where I've just said how many years is it until year 4, because This is going to be the number of compounding periods until it gets the future that we're interested in. The future we're interested in is year 4. So I'm using that same formula of find f given p. So the future value is the present 1 plus I to the power of n. So you'll get a chance to start using Excel for these calculations, but it's also important to know how to do it using the equation method. Okay, on your plate right now you've got homework number 2. That's due on Wednesday, September 4th, so you've got a little bit of extra time to work on that one, but you certainly could get an early start after what we've done today. So I'll see you in class on Wednesday.